Easy. So today, talking about soil testing, and I suppose, is there an option of taking this to the field? Is it science fiction, like a lot of these new technologies, or is it just around the corner? So just for those that don't know about our business, so we're sort of a soil and plant lab, one of the few nationally outside of the fertiliser network, so independent lab based in Adelaide and Belmont. As well as that, we do a lot of in the research space, so we've another company called Agronomy Solutions, and they've been involved in a lot of this project work I'll speak about today. Predominant role of that business is research, but we also do a lot of education and training, so predominantly with consultants and agronomists, and then also farmers as well, just get everyone up to speed on soils and nutrition and how to interpret those results. Some of our field locations last year, so we had about 30 sites in 30 projects going last year. So you can see the sites there in WA and SA predominantly. We also, there's some fantastic facilities at Adelaide University. They've got the plant accelerators, which is like a fancy glass house basically, where we do a lot of pot trial work up there in rep space. So I suppose it's important to understand what actually happens to a soil when it gets to the lab. So we're going, is there a benefit of actually taking this to the field, or is it easier just to send it off to the lab? So basically, once your soil comes from the paddock, sent in the barcoded bag, the first process we go through is they'll go into these little cups and then go in these ovens for 24 hours to dry the soil. Lab equipment doesn't like wet soil. So take that out. We can't run over 40 degrees because that will affect your carbon and nitrogen results. So everything routinely goes in for 24 hours. From there, they'll go through these little hammer mills. So what we're trying to do there is just break open all the clay lumps and get it to a nice consistent particle size. These are them there, and that's just a dust extraction system. You can imagine it's pretty dusty and dirty in that room. And then they'll go through these 2 mil sieves. So a lot of WA soils, the buckets fill up pretty quick with the gravel. The idea there is we're just taking off any gravel, any rocks, any organic matter, stubble, things like that, so it can go through to the lab. So I just wanted to throw this in at this process because this is potentially where infrared technology, has anyone come across it before? Yep. 1, 2. So it's pretty exciting technology that's been sitting in the research world for years. It's used in nearly every other industry but agriculture. What we're doing, we're using infrared, so mid and near infrared, so we're just scanning a soil and then we're measuring the reflectance. So then we're calibrating that against wet chemistry. So we're essentially scanning a soil, instant result as far as what we're trying to measure. So we could stop that process there and save a hell of a lot of work just in the lab. That's what the spectrum looks like, so all these different peaks, that's a carbon peak there, carbonate, so basically all those peaks represent something or a characteristic of different soils. So if we go back to the lab now, this is one of the most laborious steps. So we've got a nice ground sample there. Summit, good sponsor of Facey Group, so I'll throw that one in there. So we've got a nice consistent sample, but if you send a sample in, we obviously need, different tests. So there might be 6 up to 10 different tests we're doing for that soil. Each one of them will be a different soil volume or weight, and then they'll have a different extractant with them. So you can imagine if we receive 1,000 soils for that day, there's up to 6,000 different ways for that next day. They go into these 50 ml tubes, and then they go through to put the extractant with it, and then they go on end-on-end shakers for anything from 30 minutes to 24 hours. And then they're full of dirt, so they need to be cleaned up. So this is just one example. They're basically filter papers in cups, goes through and gets a nice clean sample ready to go to lab equipment. So the final step from that is going on to lab equipment. So that's called a continuous flow analyzer, and that does all the nitrogen and phosphorus chemistry. So I suppose, does this have a place, firstly in the lab, then does it have a place in the field? So in collaboration with CSIRO and Adelaide University, we've been commercialising this in the laboratory for the last 3 years. This is the robotics that is built to scan the samples. So one of the big limitations in the research world was the capacity. So this machine now will do 2,500 samples a day and 5 replicates of every one of those samples. So the capacity is huge. So just keep in mind when we start talking about the cost of the in-field equipment, you're looking at sort of about $500,000 machine there, and probably the investment into building the models, that again. So in comparison to when I start talking about the in-field costs, we're sort of looking at about $1 million sitting there. What we're testing, organic carbon, total nitrogen, particle size analysis, so going away from the whole hand texture, carbonate, cation exchange, PBI, bulk density. One of the most exciting ones we're working on at the moment is water upper and lower limits, so we can actually predict plant available water from that scan, dry grind scan. That's part of a GRDC project in New South Wales, and the lower limits have come out so far and R squared of 0.96. Just absolutely phenomenal. Just an example in the lab, so this is clay percentages. So, you know, at the moment models are running at about 0.91, which is pretty good. So what we're doing there is comparing wet chemistry in the lab to the predicted value from the mid-infrared. And the other one is plant material. So go away from soils, total nitrogen, nitrate N, phosphorus and potassium, all running at 0.92. So we're looking at a value close to 1. So that's just grind a plant sample, scan it, potentially an MPKS result back, you know, within a matter of hours, sort of overnight. So I suppose the big question everyone asks is, can we take that to the paddock? So I've got some very, very big shoes to fill today, because this is, which I'm not even going to pretend to be able to, because this is actually Mike McLaughlin's talk. I'm sure you've all heard of Mike. One of the leading, is the leading sort of soils nutrition researcher in Australia. Les Janik, so he's sort of been working on IR stuff. He actually works for APOW now, developing all our infrared side of things. Michael Zerner from Adelaide Uni, and then Sean, my business partner in Agronomy Solutions. So this was a collaboration between CSIRO, Adelaide Uni and Agronomy. So I'll go straight to the key points so you don't forget, because we're getting close to beer. It's doable, 100% doable, and it's not too far away. It's got some challenges. Really, it's reliant on cheap sensors, which we'll go through the costs of the sensors in a minute. But there's new sensors coming online all the time. The infrared's looking the most promising, but the key message with any sensing technology is it needs evaluation before we can adopt it. And don't believe the marketing material that's out there. You know, we're getting so bombarded with stuff now, particularly from America, with iPhone apps. Just take a photo of your soil, get a result back. Sensors claiming sort of phenomenal results for phosphorus, all those type of things. But one of the key issues with the sensing technology at the moment is the big ticket items. So MP, K and S we're really struggling with. So it's going to be more of a soil characterisation tool, particle size analysis, you know, typically a $70 test we can do for basically routinely. Carbonates, cations, ESP, all those type of things. Where we see it really going is creating a more intense sampling strategy. So not necessarily spending less on the testing, it's going to allow us to do more and create more data, which is all about, is gathering more data. So if we go to a traditional plan, if we're looking at the lab analytical costs, like typically we might go out and do this zonal approach at, you know, $60 to $90 a sample. If we're looking at that, you know, we're $300 a paddock. If we go back, which I hope no one's doing, and do a transect, well, you know, we're back to 60, but it's not really telling us a lot. If we go to what we should be doing, which is done commonly, you know, this is how they soil sample in America, Canada, these precision grids type sample plans, you know, we might be looking at 45 tests in there, your analytical cost all of a sudden goes out to $2,700. So if we can create a tool whereby we can use this infrared technology to do that intense sampling at the same price, then we're going to be on a winner. Some of the ones you might have seen, the Veris on the go, pH mappers before, technology out there in the industry at the moment. Near infrared, you know, we're getting down now where they can be little size of your palm. Mid-infrared, which is the one we use in the laboratory, they use this in the environmental space for looking at soil contaminants. And X-ray, XRF. Now, XRF is a bit more promising because it's picking up some of the macros. Looking at costs of those, we can get down to as little as $1,000. This Spectral Evolution, which is a handheld NIR, was sort of $80K. This instrument here, another one, $1,000. Then the mid-infrareds, you're running sort of around that sort of 60 grand. So it's a pretty big investment, obviously, or it basically rules it out for a grower to put one in the glove box of the ute, or an agronomist to sort of run around with them. So what Mike's project was doing is comparing, so this isn't in the field, but it's comparing these handheld instruments compared to the lab instrument and seeing where they stack up. What the group looked at was pH-EC, particle size analysis, cation exchange. You can read the rest there. Basically the key message is we've got the R squared running up the side here. So look at the lab instrument is in the black, and then so this is the more expensive MIR guns. You can see total carbon's always really good. We can do that very well. Against Walkley and black, the handheld instruments actually performed a bit better. But without going through them all, you can sort of see that they all perform pretty similar. That's with the more expensive MLR guns. If we go to the NIR, remember the $1,000 jobs? That's these down here. So the Spectral Evolution, remember that was 80K. These $1,000 one down the bottom, you can see just doesn't stack up against the more expensive equipment. So basically, key message is it can happen, or these handheld guns perform as well as the lab equipment. So we don't think it's really too far around the corner. So an example where we've gone out looking at trying to map PBI on a couple of our trial sites. And the other one we're looking at N content, so scanning crops at key growth stages for nitrogen management. We think that's got sort of a lot of merit because with all these satellite technology, you know, these things coming on, one thing we've got to remember is they always need to be ground truth. So potentially creating really cheap, quick options to ground truth these technologies. So PBI, this is obviously a calcareous soil in South Australia. So you can see we've got PBI ranging from 47 to 110. What drives, how's the IR picking that up? These peaks here, PBI is generally driven in your soils, acid soils, by aluminium and iron oxides, and it's using carbonates in the calcareous soils to predict that PBI result. Sorry, we've missed a few slides there, I think. Something's gone haywire. So, picture a nice graph there with a, that's all good. So what we did go across one site and 3 sites, using that mid-infrared. So one of the issues, this is obviously one of the good sites, is soil moisture. So in the lab we take the moisture out, so we dry grind, it's gone. But we got R squareds up over 0.9 in the field, and then when we corrected for moisture, it went up to 0.96. So that's on one trial site, and that's a good example. There's some that are down at that 0.5, 0.6, but we just need to work out what's driving that. But essentially, it's essentially a paddock mapping tool for PBI already nearly ready to go. Just got to work out what's happening with this moisture that's causing some issues at some sites. The other one which we think, particularly with this with the satellite imagery, is being able to go out into a crop and just shoot the crop and look at, in this case we were looking at water-soluble carbohydrates and nitrogen content. Issue with NDVI is, you know, it doesn't work once you get that saturation or cover up. So what this project's doing was basically rate response trials, just applying 0, 25, 50 and then 100 kilos. So we had varying N rates replicated across 2 sites. And then we used the NIR gun to shoot them in crop at different growth stages. So this was it here. This is Kenton Porker from he's with Sardi out scanning the plots. You can see so this range from here to back to here is what NIR will pick up, and then from that, from about I think it's 8,000 off the top of my head through to here is the MIR range. You can see with NDVI it's really, really tight range. So it's just looking essentially at that little narrow spectrum compared to what these guns are. And the unit we're using was 10 to 15 grand, so probably affordable for a consultant or agronomist to put in the ute and run around who's sort of servicing multiple clients. Sorry about that. So anyway, there was GS30 scanning and GS40 scanning. Worked very well across those 2 sites. So R squared's in the sort of 0.8 to 0.9 type range. So essentially all that needs is more data behind it, and it's a tool we could take to the paddock. It's pretty hard going out to try and validate imagery maps and obviously plant tissue testing and trying to get the right growth stages or doing biomass cuts, those type of things. So key message, it worked well. So we've got another project hopefully going to get up soon to basically expand that across more sites and more regions. Just another quick one, what else is out there? I spoke about the X-ray fluorescence. Very good at measuring total elements in soil, so like total phosphorus, total nitrogen, total potassium. It's absolutely brilliant. You can see here P concentrations, total P 0.92. The issue is totals don't really mean a lot to us with making agronomic decisions. Another just quick one, real quick, because we're out of time, but you might have seen these sort of soil scan type infield nitrate testers. GRDC, we contracted us last year to just test them against lab testing and see how they stacked up. Pre-sowing it was terrible, and then in season it got better. But what we found we had to do with a couple of agros we were working with, they actually took the soils home to their shed, dried them out, and then retested them, and it got better. So potentially that's not too far away either, just needs some improvement with the probes. That's about it. So it's not too far away, I don't think. The lab side of infrared's only just developing, so that's going to start to generate a lot more data for us. And then I think, putting a time frame on it, it's probably not in the next 5 years, but as that sensing technology becomes cheaper, I think we can make something work.